Vector analysis. We're going to describe motion in terms of an object's position, velocity, and acceleration. All these three parameters are of course vectors. And as I said, we will throughout this course describe the motion of an object, describe motion of an object using these three parameters. If an object is, well, let me do an example on an xy plane. Let us say this is the origin. Let us say the initial position of an object is here. So this is initial position. The initial position vector would then be a vector that starts at the origin and points to the initial position, of course. So Ri is the initial position vector. Similarly, if the object ends up at this position, let's call this position final, then the final position vector is such, Rf. So that's the final position vector. Let me open up some space on my screen here. Good. So Ri then be the initial position vector, and Rf of course is the final position vector. So we now define displacement for the object, displacement, which is a change in the position vector delta r, delta signifying a change of course. We define that as Rf minus Ri. Notice that this here is a vector subtraction, so you need to follow the rules for vector subtraction. I'll go over vector subtraction, vector addition in a later section. So the displacement vector delta r would then take the form here. So this is our delta r. That's the displacement vector for the object. And if we know that the object undergoes this displacement delta r in time delta t could be 1 second, 0.1 second, 1 minute, 1 day, whatever. Then using this information we define average velocity for the object as the displacement that it has gone through divided by the time that it has taken for the object to undergo that displacement. Please note that here we are dividing a vector quantity delta r by a scalar time. Therefore we end up with a vector. Velocity of course is a vector, but it's important to remember that the direction of the velocity vector is always in the same direction as the displacement vector, by virtue of the fact that we are dividing delta r, a vector, by a scalar. In multiplying, dividing a vector by a scalar, we affect its magnitude but not its direction. Therefore the velocity, we can confidently say that the velocity vector it points in the same direction as the displacement vector. An important thing to remember for later on in your analysis. Okay, let me do another plot. So this is my XY plot. Let's say the object is here. I'm going to call this position 0 at time 0, for example. So this is my R0. Notice that the subscript for my position vector corresponds with the label that I assign for each position. So here's position 1. So therefore this would be R1, and let's say this is position 2, and this is of course R3, position vector, oh I'm sorry, R2, my apologies, position vector 2. Now we can go ahead and say that the displacement vector between positions 0 and 1, so that's the displacement of the object from going from 0 to 1, is defined as R1 minus R0, and it's this vector right there. So this is delta R01. Similarly, delta R1 to 2 is R2 minus R1. That's this vector right here. Okay, delta R1, 2, and assuming that delta t is the same in each case, so it takes delta t seconds for the object to undergo these displacements, then we can come up with the velocity vector in between positions 0 and 1 as delta R01 divided by delta t, and velocity of the object between 1 and 2 is delta R12 divided by delta t. So the velocity vector, so this would be delta R0, I'm sorry, delta, let me start again, made a mistake. So this is velocity, wrong color pen. This is velocity 0, 1, and this is the velocity vector 1, 2. So as you can see, the object has a change in velocity in between going from 0 to 1 and then going from position 1 to position 2. And this change in velocity delta v is essentially is a vector quantity, and is given by velocity 1, 2, which is the final velocity that the object has minus the initial velocity that the object has. Okay, so that's a change in velocity. Once again, this is a vector subtraction. Let me pause here and perhaps go over vector subtraction with you quickly. If you have, first of all, a vector, as you know, is has both magnitude. So here's vector A. It has both magnitude and direction. So the magnitude being the length of the vector, and the direction, the particular direction that is pointing in a given reference frame. And the nice thing about the vector is that you can take a vector. Oops, I couldn't. You can take a vector and you can transport it in space. So long as you don't change its direction nor magnitude, you can transport in space and it's still the same vector. You have not changed the properties of a vector by transporting in space. Something that's going to be helpful for us in our analysis down the road. Now, if we have a vector A and we have another vector, let me draw another vector here, vector B. Okay, these are two vectors. First of all, what is A plus B vector addition? Probably the best technique to use is a parallelogram technique, in which you would take the two vectors and kind of join them tail to tail, and then draw a parallel line from the tip of A. Draw a parallel line to B, and from the tip of B draw a parallel line to A. So you end up with a parallelogram. Parallelogram is a geometric shape, as you know, that has two parallel sides. Now the long diagonal here, so if you start at the tail and go along this diagonal, this vector, the blue vector that I've just drawn, is A plus B. So that's the sum of the two vectors. So A plus B is the diagonal of the parallelogram that you obtain by going from the tails, the origin rather, to the opposite corner. Now as far as A minus B goes, A minus B is a vector that, let me see which way it goes. It starts at the tip of B, and goes to the opposite corner. So this is the vector A minus B, and the vector, let me do it in red, B minus A is vector the opposite to A minus B, so it's the same magnitude as A minus B, but it's pointing in the opposite direction. So this here is A minus B. So this parallelogram technique is a quick way to graphically figure out vector additions and subtractions. Later on, when we decompose vectors using the trig functions, then we do our vector algebra, of course, by adding and subtracting the each vector component. So in this case, we have delta V1, I'm sorry, V01 and V12, the two green vectors that I've indicated in this diagram. Then if I were to redraw them at the corner here, so this is V01, and if I draw V12 here, then assume that the tails are joined. Then by doing the parallelogram technique, you see that we can create this parallelogram right there. And if you are interested in this entity here, which is V12 minus V01, then it's a vector which is going like this. Okay, so from the tip of the second vector that we are subtracting to the tip to the opposite corner. So this little fellow here is our change in velocity. Okay, now having figured out the change in velocity delta V, if you know that this change in velocity took place in over time period delta t, now we can define an acceleration vector A as delta V divided by delta t. And once again, please note that we are dividing a vector by a scalar. Delta V is a vector, delta t is a scalar, and we end up with a vector A, and the vector A is points in the same direction as the delta V vector does. Therefore, the acceleration vector in our case, in this case, also points along delta V. So this is the acceleration vector. Okay, so the velocity vector points in the direction of the displacement vector, and acceleration vector points in the direction of the change in the velocity vector. Okay, continuing on, let us do a couple of examples of one-dimensional motion. First, let us look at motion, let's say, of an object along the horizontal. This is the x direction. We define the positive end of our axis. Let's define the origin. Let's say the object starts here. This is position 0. And then it's this is position 1, position 2, position 3, position 4, etc. So the position vectors for the object, I'll draw it at the top here. So position vector for position 0 is, well, it's just a dot. There is no position vector. 0 magnitude. This is position vector R1, and this would be R2, R3, oops, sorry, and R4, etc. So the displacement vectors, let me do displacement vectors in blue. This would be displacement vector delta R01. This would be delta R12. This would be delta R23. This is delta R34. And velocity vectors, they point in the same direction as the displacement vectors. So these would then be our velocity vectors. Let me do it at the bottom here. So this is velocity 0, 1. Velocity, so we can just call this velocity excuse me, velocity 0. So that's the velocity that the object has position 0. This is velocity 1, velocity 2, velocity 3, etc. Now if you notice, if we also want to do the acceleration vector, and I'll show it in red, you look at the difference between v1 and v0. That's one division. Therefore the acceleration of the vector, the acceleration that the object has is one division. So this is a1, and then we have, this would be a0. Similarly, the acceleration is constant throughout to a3, etc. So it's only one. So at each position, the velocity increases by one division, as you can see. Therefore, the acceleration vector is constant in magnitude throughout. Due to this acceleration, the velocity increases, of course, in each position. Hence, the displacement increases as the object moves forward. So if we have a positive velocity vector and a positive acceleration vector, in the example that we just did, both acceleration and velocity are positive. They're pointing towards the positive of the axis. This indicates that the object is speeding up. If we have a positive velocity vector but a negative acceleration vector, this is an object slowing down. If we have a negative velocity vector, that's an object moving backwards along the x coordinate, but a positive acceleration, That's also an object which is slowing down. So it's moving backwards, but the object is slowing down as it's moving backwards. And similarly, if the velocity vector is negative and the acceleration vector is negative, that's an object which is speeding up, going backwards. Okay? So the negative velocity indicates that the object is moving. The velocity vector is thus pointing back as a negative velocity vector. And if the acceleration vector is also negative, then the velocity vector grows bigger and bigger as time goes by. So that's a speeding up, an object speeding up in the negative direction. Let me create some more space. If we take a look at an object's motion in the vertical dimension, once again, if you throw an object up in the air, so let's take a look at the y axis now. That's my origin. Let's say I take a coin and I throw it up. This is the instant when I release the coin. Let's call that 1, position 1. It's the position of the coin after some delta t later. And this is 3, this is 4. It comes to a stop, let's say here, and then it comes back down. So going up, this would be our, actually let me stick with the convention that we used. So this would be the displacement vector, delta r1 for the object. This is displacement vector delta r2, delta r3, etc. So as you can see, the velocity vector, the velocity of the object v1 is defined as delta r1 divided by delta t. So this would be our v1, v2, v3. The velocity vector is growing smaller and smaller in magnitude. That is because there is an acceleration vector which is pointing in the reverse direction, and it's constant in magnitude at all times. And this acceleration, if you're talking about motion in the vertical direction, of course this acceleration vector is equal to minus a g, right? Where g, the magnitude g, is 9.81 meters per second squared. G is always a positive number, whether it assumes a positive or a negative sign depends on your choice of axis. In this case, since we chose y to be pointing up, the acceleration is negative g. Had we chosen the y-axis pointing down, of course, then the acceleration would have been positive g. So please do remember that g is always a positive number, 9.81. Now, I said that the object comes to stop here, so that's position 5. Let me bring this position over here. This position 5. Positions, and then it starts coming down. So then we have position 6, position 7, position 8, and position 9. Now you see the displacement vector is switched direction. The object is coming down. So has the velocity vectors. So velocity vectors are now pointing down and they're growing in magnitude at each frame, but the acceleration vector has remained the same. Okay, that's because the acceleration acting on the object through this vertical motion is only due to the gravitational force, and hopefully the gravitational force doesn't change during the time that we throw the object up and it makes its way back. At this position 5, We all know that the object comes to rest, so velocity of the object is 0. However, please note that the acceleration is still minus g. So even though the object has come to rest, the acceleration is still minus g. This point is called a turning point. Turning point is when the object reverses its direction. So it's moving up, it comes to stop, and then reverses direction and heads back down again. Okay, so this is a motion diagram that we just did. Now we can go ahead and do a position versus time plot from a motion diagram. So in this case, if you look at the position of the object, so this is the position of the object versus time, and let's just divvy it up. So that's our origin, so that's 1, 2, 3, 4, let's say seconds, etc. Don't forget your units, and position, let's call it in meters. So this would be 1, 2, 3, blah blah. So the position vector that's throwing the object up, how the position would change is it would start increasing fast and then come back down again. Okay, so what I'm showing here is that the object starts going up, it reaches a height of, let's say, 3 meters, and then heads back down again to 0. So this is a position versus time plot for the object being thrown up. Now if we said that well, let me back up. The slope of position versus time graph gives you the velocity of the object. Okay, so in this case, of course, we have a curve, but as you know, the slope, if you're interested in slope at this point, the slope of a curve at any point is equal to the slope of the tangent to the curve at that point. And as you can see, the slope of the curve on the way up decreases as we go up. So we have a steeper tangent here, than steeper tangent at this point than we do at this point, which indicates that the velocity of the object is getting less and less till it comes to the maximum height. Here we have a horizontal tangent, which means velocity is 0, since the slope equals 0 at this point right here. Okay, now on the way down, let me use color red. Now on the way down, the slope of the tangent is getting steeper, but it's a negative slope, which means that the velocity is now a negative velocity on the way down. We know that it is, and it's getting steeper and steeper, i.e. the velocity is increasing more and more as the object falls down, which is consistent with what we talked about earlier. So if you were to plot the velocity of the object, v in meters per second, versus time in seconds, you see that starting off, we have a high positive velocity. Then as the object makes its way up, its velocity decreases till it hits the turning point. So this is turning point, velocity is 0, and then the velocity starts increasing, but in the negative, so in the negative direction. So It's a negative number. So the velocity versus time plot for this object being thrown up and heading back down would look something like this. And if you recall, we said acceleration is delta v over delta t. Now, in the limit of delta t becoming smaller and smaller, then essentially in the limit of delta t getting smaller, then your acceleration is given by the slope of velocity versus time graph. So here we have a straight line which indicates that the slope is constant, i.e. The acceleration that we have is constant. This is a negative slope, it's heading down, and as we know, we talked about the acceleration being equal to minus g, so things are consistent. So it's a constant slope. So if you do rise over run, this is our delta v, this is our delta t. So delta v over delta t is essentially, as I said, the slope of the time of the velocity versus time plot, and we have a nice constant negative slope in this case. So now you can go ahead and do a plot of acceleration, meters per second squared, versus time in seconds, and the plot, well, it's looks like this. So this is minus g, so that's 0, that's minus g. It's constant throughout. So just to refresh again, velocity we said is change in displacement divided by delta t, and in the limit of delta t getting smaller and smaller, then the velocity is defined as the slope, which is dr dt. So if you're dealing in one direction, the velocity in the x direction is dx dt, that's a derivative, and velocity in the y direction would be dy dt. Okay, that's the slope of this position versus time plot. And similarly, acceleration we defined as change in velocity over delta t, and once again in the limit of delta t getting smaller and smaller, your acceleration is given by dv dt. So acceleration along the x would be dvx dt, and acceleration along the y direction would be dvy dt. Okay. A couple of hints as far as problem solving. I strongly urge you to read the problems carefully. Having read the problem, do a pictorial representation. So draw a picture, nice picture of what's going on. If you're talking about a car driving to the right along the horizontal, define your axis, define your origin, show the car's motion. Here we have a car going at constant velocity over these two periods, and then let's say it starts applying the brake and comes to a stop. Okay, so 3, 4, 5. And then go ahead and define your symbols. So you can basically say t0 is 0, t1 is 1 second, t2 is 2 seconds, etc. If you know the velocities, so v0 let's say is 15 meters per second, So you go ahead and define your v1, v0, v1. Write down all the knowns that you have. If you don't know it, define the symbol, but leave the value blank. And acceleration, well, acceleration that we have here is 0. There is no acceleration because the car up from here to here over this region has 0 acceleration. It's not accelerating. A1 is 0, but A2 is a negative acceleration because the car is now applying the brakes and slowing down over this region. Okay, and we do know that finally final position V5 is 0. So what I'm doing here is essentially doing a pictorial representation, writing down the pertinent information, defining my symbols, and go ahead and use up half a page to do this. It's critical that you do this in a clear manner. It will help in your well, working through the problem. And it's only after you have done this